This firefighter is built to swoop onto lakes and rivers, fill up, then hit fires with water bombs. The Combine is a mobile processing plant that spits out 200,000 kilos of corn in one day. Hold your breath. The wind tunnel cranks out a typhoon to make sure the skyscrapers we live and work in stay upright. The 50 cal machine gun has been a military favorite for 90 years, thanks to its deadly reliability. Let's take the lid off these machines and see how they work. This is the Bombardier 415 water bomber, also known as the Super Scooper. It's a flying boat that's the backbone of firefighting missions around the world. Whether dousing blazes in remote Canadian forests or protecting hillside homes from raging California wildfires, it's proven itself to be one of the most powerful aerial firefighting machines ever made. It can pick up over 6,000 liters of water in one scoop. This translates into over 100,000 liters an hour being poured onto a nearby fire. 3 tanker trucks worth. Let's see how it works. To make a water bomber, all you gotta do is combine the floating ability of this, the cargo capacity of this, the maneuverability of this, and then throw in a little bit of this. A big challenge for engineers. The 415 does it with a wingspan almost as long as a 737's, 2 powerful variable pitch turboprops, a rust-proof aluminum hull, and massive water tanks fed by hydraulic rams. The first challenge for the 415, get airborne quick, even from the smallest runway. These machines have to be able to get up and down fast on land and on water. That happens thanks to these wings and these engines. The wings have a surface area larger than a jumbo jet's for extra control and lift. They're designed with a highly arched shape or camber and huge flaps. These give the 415 better stability and lift at slow speeds. So much lift that its tail section is oversized to help keep everything balanced. The power for this machine comes from 2 2,500-horse turboprops. A turboprop engine is simply a gas turbine. Inside, the air is compressed, mixed with jet fuel, and set on fire. As it burns, the air expands. The expanding air spins a turbine that spins a drive shaft, which turns a gearbox and the propeller. Attached to the front of the engines, these propellers have variable pitch blades. The blades' angles can be changed. This allows the engines to hit high RPM while the plane is parked, effectively revving the engine while in neutral. Then, with a change in pitch, pilots can blast the plane off the runway. This lets the 415 take off at just 150 kilometers an hour, about half the minimum takeoff speed of a passenger jet. And that high power at low speeds comes in handy when it's time to hit the water. As the 415 approaches its target, it lowers the flaps and reduces the pitch on the propellers. This slows the plane down to about 140 kilometers an hour, a speed that would cause most other planes this size to stall and fall. The 415 is now a boat with wings. Crafted from marine-grade aluminum, it even has special airtight compartments to keep it floating if it hits something and gets punctured. When collecting water, only the bottom few centimeters of the craft get wet. Technically, it's still flying, and the pilot still has maximum control. On the water, these machines can swerve to avoid obstacles, or even gather water from a winding river. And these water scoops are way too small to suck up a scuba diver. Hydraulics push out the scoops when it's time to collect. The plane's speed is all that's needed to ram the water into its tanks. It fills up in just 12 seconds. Then the scoops retract, and it's takeoff time. The 415 can climb at angles that would knock other planes from the sky, which is what this machine needs to fight fires. If it's a small fire, the scooper just dumps directly onto the blaze. It flies low, just above the target, opens its 4 doors, and dumps its entire load in 1 second. Dropping over 6 tons of water, the pilots gotta be accurate. That amount of liquid could cause some serious damage to someone on the ground. But even that much water is no match for big wildfires that can burn at temperatures over 1,000 degrees Celsius. So the 415 changes tactics and injects the water with foam stored in these tanks. The foam is a synthetic biodegradable fire suppressant. When the 415's doors open, the supercharged water hits the air and transforms into a thick foam, blanketing an area the size of a football field. The foam sticks to trees and the ground for up to 30 minutes and creates a wall of water. With a few well-aimed shots, a single 415 can create a 2-kilometer-long fire break. Its doors can even be programmed to release one at a time, spreading foam over an even greater distance. And since it can pick up water from almost any source, even a river just 2 meters deep, this machine can load up, dump, and refill in as little as 2 minutes, which translates into 100 dumps in 4.5 hours flying time. Over 500,000 liters of water. Despite its ungainly appearance, it really is a beautiful flyer. And once it gets airborne, there's no doubt about its primary purpose. This is one serious firefighting machine. This is a combine harvester. A machine that harvests grains like wheat, soy, and the king of the modern field, corn. It's probably the most important machine working on farms today. And without them, there'd be a lot less food to go around, and a loaf of bread would cost a small fortune. Corn is a linchpin of the modern food chain. It shows up in almost everything we eat, from sweeteners to farm salmon. And a combine this size gets through about 80 acres of corn in a day. You'd need hundreds of experienced pickers just to cut that many ears by hand. And that's only one part of the operation. This machine takes less than a minute to strip and collect over 2 million kernels of corn. Let's see how it works. A combine gets its name from merging or combining a bunch of jobs that used to be done by separate machines or by hand. When harvesting corn, it cuts the crop from the ground, separates the stalk from the cob, and then sends those cobs into a rolling drum to strip off the husk and kernels. It costs hundreds of thousands in fuel, seeds, and fertilizer to plant this crop. And once it's ready for harvest, farmers can't afford to waste any of it. So this machine has to get it done fast without wrecking the crop or itself. First up, remove the ears of the corn from the stalk. For that, you need a special attachment called a corn header. It snaps easily onto the front of the machine. The header has gathering points that fit between the rows of corn. The fields are planted to mesh perfectly with the headers. In this case, rows of 6. This allows the combine to go back and forth with maximum efficiency, gathering as much corn as possible with each pass. With the help of careful planting and the right header, a combine can harvest about 400 tons of corn in a day. The stalks are channeled toward pairs of chains. Teeth on the chains push the stalks into 2 spinning rollers. The rollers pull the stalks down. The cobs are too big to fit, so they snap off. Below the rollers, spinning blades turn the stalks to mulch, and another set launches them out the back of the combine. Knocking the heads off these things is only part of the challenge. Next up, stripping the seeds. This auger spins the cobs toward a central conveyor belt that carries them to a curved metal grate called a concave. It wraps around a meter-long rolling drum. The rolling rubs off the husk. Then the sharp edges of the concave strip the kernels from the cob. The kernels fall onto a vibrating grate. This powerful fan blows air up through the grate, and the air plus vibrations force the plant debris and husks to the top, while the kernels fall to the bottom. An auger carries the kernels up to a grain bin, while the rest of the material is sent back onto the field, where their nutrients are returned to the soil. When the grain bin is full, it simply dumps its load and goes back for more. This machine makes it look easy, but it has to constantly adjust to different conditions to find the perfect speed. If the combine goes too fast, it loses yield because this processor on wheels can't keep up with the corn. And too slow is, well, too slow. So as it works, sensors feed information into the cab. The flow sensor reads grain impact force from the top of the clean grain elevator to calculate the volume of corn. Grain moisture and temperature are measured with this sensor. An electrical current flows from the sensor fin through the grain and calculates its humidity. All this information is fed into the cab to keep the operator constantly updated on how much corn is being harvested. And that's not the only data at work up here. These machines never get lost. The route they follow is controlled by an onboard GPS system that ensures no-fault harvesting. The combine is a perfect blend of farming technology and mechanical know-how. An ultra-efficient machine that does everything we ask of it to put food on our tables. A wind tunnel is a machine used to research the effects of air moving past solid objects. For centuries, they've helped scientists and engineers experiment with all kinds of subjects. From understanding the principles of flight to making faster race cars. Weather simulations inside wind tunnels can also provide critical information for building safety. This is more important now than ever, as buildings have become taller and more complicated. The National Research Council's closed-loop wind tunnel outside Ottawa, Canada, is a perfect spot to test buildings. This world-class facility boasts a 9,000 horsepower motor that drives a 12-meter fan. Big enough to create a typhoon, which is why it was chosen to test this skyscraper, the 128-story Shanghai Tower. The Shanghai Tower is a city on its own, with over 4 million square feet of living and working space. And it sits smack dab in the middle of Typhoon Alley. Wind causes towers this tall to lean and sway. They can lose windows, and worse, fall over. So they can't be built without input from the wind tunnel. Let's see how it works. Turn over big engine, spin huge fan, create wind. That's easy enough. But when testing this tower, even a 1/85th scale version, you can't just blow a fan on it to get the data you need to make it safe. Sensors are connected to the model so that engineers can perfect its shape before they begin construction. And the wind tunnel has to be able to create many different types of conditions to mimic the real world and make the testing worthwhile. To replicate a steady flow of wind, fixtures in the tunnel are as smooth as possible to help control turbulence. The fan actually sucks air away from the model, around the donut-like structure and back. Every time the air circulates through the fan, it picks up speed. It also picks up a lot of unwanted turbulence. An uneven airflow ruins testing. So the less turbulence there is, the better the results. Turning vanes in the corners help smooth out the flow. But that's not enough. So the tunnel draws heat from the air with fans in these cooling towers. Then, the air passes through mesh or honeycomb screens that further calm it. And finally, it passes through a settling chamber, where the swirling air currents spread out and subside before carrying on. Once the air is smoothed out, the wind tunnel needs to create its own custom turbulence to simulate real-world conditions. And they use a net to do it. The netting creates turbulence that mimics airflow through tall buildings. Now we're ready to see what the building will do in a windy city. The fan in the wind tunnel takes about 5 minutes to hit top speed and deliver 200-kilometer-an-hour winds into the tower's outer skin. The first design challenge measures structure strength and dynamic response, which includes how far the building sways back and forth. To measure these, the model is securely bolted to a floating table. Beneath it lies a room packed with sensitive measuring devices. As the wind pushes against the building, these weights move to counter the force. When the table is pushed in one direction, the weights move the other way to keep it balanced. The further they move, the greater the force. It's all linked to a set of levers that come up with the final measurements. This data tells engineers what kind of damping systems to install in the tower to control excessive movement. Now, wind changes direction all the time, but the model is secured to its base. So the whole table rotates into the wind to measure every angle of attack. Now the machine has to test the integrity of the building's outer surface. These tiny holes connect to hundreds of tubes, and those connect to pressure sensors that measure wind load. As air flows around buildings, it creates small swirling currents like water flowing around a rock. This can put tremendous strain on materials as the air currents break from the building. Sensor data lets builders know where to strengthen materials or install special fixtures to disrupt wind flows. Small foundations, great height, and odd shapes. Today's towers could never make it from the architect's imagination to the real world without the wind tunnel. A machine that keeps urban residents high, dry, and safe, even when a real typhoon hits. Meet the Browning M2 50 caliber machine gun, affectionately known as Ma Deuce. The first version of this machine arrived on the scene at the end of World War I. Its simple, reliable design and its ability to smash through steel and concrete is why the M2 is still being used by armies in every corner of the world. Let's see how it works. Bullets, linked by small metal clips, are loaded into the breech. When you cock the gun, a round is snatched up and dropped into the chamber. Now the firing cycle begins. On the M2, the trigger is pushed. This starts a chain reaction that sends the firing pin flying towards the back of a shell. When it hits, a primer is ignited, setting off a small explosion. Up to 55,000 pounds per square inch of force is generated when the shell ignites in the chamber. The force of the explosion slams the breech bolt back. This action forces another round into the chamber, and the process starts over again. All driven by the energy exploding from the shell. After the bullet fires, the extractor grabs the rim of the empty shell, and a spring-loaded ejector punches it out the bottom of the gun. The M2 is air-cooled. Its open breech allows heat and smoke from the firing cycle to vent. Inside the barrel, a process called rifling has grooved a pathway roughly 1 turn every 30 centimeters. As the bullet is forced through the barrel, it follows the corkscrew path. The path puts a spin on the bullet that maximizes its flight accuracy and increases the damage on the receiving end. The bullet easily breaks the sound barrier, exiting the barrel at 900 meters per second. That's over twice the speed of sound. Not bad for a round this big. And the M2 can fire a bunch of different types of ammo. Standard ball, tracer, armor-piercing incendiary tracers. These guys have strengthened casings and a hard nose to punch holes in thicker armor. The tracers leave a flash of light from a small pyrotechnic charge in their base. Once ignited, it burns like a firework, making the bullet visible to the naked eye. Tracers are usually loaded 1 in every 5 rounds. This helps the gunner visually follow the path of the bullets. And the M2 is capable of firing up to 500 rounds per minute. But at that rate, the barrel would quickly overheat and begin to warp. So in standard combat, the gun is fired at a rate of about 40 rounds per minute, in short bursts. Uncompromising firepower and combat reliability are just 2 reasons why this machine has withstood the test of time.